Hello and welcome to Factive, your home for knowledge in 5 minutes or less. My name is Sean, so sit back, relax, grab a coffee, because today we'll be learning about nuclear fusion. And who knows, after this video, your friends may mistake you for a nuclear physicist. Alright, let's get started. Have you ever wondered how stars work? Well, we can think of these celestial bodies as self-sustaining fusion reactions. Okay, but what's a fusion reaction? Well, as the name implies, a fusion reaction occurs when two smaller atoms fuse to form a single larger atom. In our sun's case, deuterium and tritium, both hydrogens with 1 and 2 neutrons respectively, would fuse to form helium-4, a helium with 2 neutrons. Unlike nuclear fission, which is the process behind conventional nuclear energy that involves the breaking of atomic bonds, nuclear fusion is the result of the combined atom having less mass than the total mass of the smaller atoms. To put it in simpler terms, the sum of the parts is greater than the whole, leaving a little bit of mass left over, usually a rogue neutron, that is converted to energy. Okay, but how does that work? Well, according to our friend Einstein, energy is E = mc squared, or mass times the speed of light squared. So even if the leftover mass is small, the speed of light is immense, especially if you multiply it by itself. So if fusion were food, the result would be a donut hole larger than the original donut. I could live in that world. So far, so good. Let's get fusing. Well, not so fast. Nuclear fusion requires an extreme set of circumstances. The main reason comes down to electromagnetic repulsion. Did you ever play with bar magnets as a kid and try to connect the poles north to north or south to south? You would have noticed they repelled each other. Now, imagine taking two of the world's strongest magnets and trying to do the same. It's not going to happen. The same principle applies at the atomic level. Fusion requires its fuel to be heated to an excess of 100 million degrees Celsius, roughly 7 times hotter than the sun's core, to overcome the repulsive forces and coerce the atoms to fuse. And if that wasn't enough, the particles must collide at high speeds, like shooting 2 BBs at each other from 200 yards and hoping they smash into each other. Oh, and the BBs are traveling 4 million meters per second. The improbability makes recent breakthroughs in fusion that much more amazing. If you're following along, something I said towards the beginning of the video just doesn't quite add up. Stars like our sun are powered by nuclear fusion, but recall that nuclear fusion requires a temperature hotter than our sun, and the reaction itself has a low probability. Well, if that's the case, then how has Earth's sole source of heat and light not just fizzled out by now? Well, it turns out that the sun has a leg up in the quantum realm due to the sheer pressure, density, and energy content of the sun's core. The rules for self-sustaining fusion are bent. So even though the probability of fusion in the sun's core is still minuscule, there are enough interactions, some billions per second, to keep the sun ticking along. Here's to overwhelming probability. Well, that's the end of today's video. For some deeper dives into this topic, check the links in the description below. Also, leave a like and a comment about what Factive topics you would like me to cover. Until next time, have a good one.